whole year right now, aren't we? Okay. Charge. From your 3rd grade science project, you know that like charges repel, opposites attract. That was also a really good Paula Abdul song back in the day with DJ Scat Cat.
Can you sing it?
An animated cat that danced with her in a music video.
That's so cool. Can we watch it?
Opposites attract.
That's actually not true.
So we all know this from 3rd grade. You really don't need to copy this down word for word because you probably copied down word for word in 3rd grade. Okay? Good. But what you do want to remember is this, that having a negative charge just means there's an excess of electrons. Okay, there's more electrons than protons.
Yeah.
Simple enough. Okay? Having a positive charge means you have a deficiency. Okay? Okay.
I think
You just took your whole AP Chem exam in the opposite direction, didn't you?
my washing machine has this, right?
I don't know.
Oh, well, no, because we got a new one, and it's like something high efficiency, deficiency.
That's high efficiency for being more efficient.
Oh,
okay.
So you said you meant
Not deficiency.
efficiency, same thing.
Efficiency is
A deficiency, as in not enough electrons as protons, will give you a positive charge. Okay? We got that? You can probably pause it now.
Yes. Pause it?
Yeah. Now, you don't copy this down, please, but just understand that positive and negative charge, it's not that the charge is created or destroyed. It just means that electrons are being passed back and forth. Okay, so if you rub a balloon in your hair, okay, it's going to pass electrons from one side to the other, and one will be positively charged, one will be negatively charged. It's not that you've created electrons. Hold that thought. All right. Just a quick side note to understand is that actually electros, the word electron, let me go check. Let's pause for station identification here. The idea of electricity really comes from the word electros, which was just the word for amber. And it was because they realized that rubbing this beautiful jewelry against their clothes would create a charge. Okay, so the whole idea, realize that electricity, what we all know about electricity, started from just the rubbing of objects. That's the first way we actually noticed it. I mean, we didn't know that what lightning was at the time. So the first human interaction with electricity was just the rubbing of material and passing the electrons back and forth. Okay. Now, here's a formula you need to know. This actually should look similar to something you've done already. K, Q1, Q2 over R squared. We haven't dealt with those letters before, but does that formula look familiar?
Chemistry, yeah.
It's exactly, yeah. It's analogous to the other force, for gravitational force. So this is a force of charge, electrical force, okay? Before it was gravitational force, but it's set up the same way. The force between two objects will be equal to some kind of constant times something about those two constants divided by the distance between them squared. Where in this case, instead of capital G, that's 6.67 times 10 to the negative 11th, we have lowercase k, 9 times 10 to the 9th. I want you to think about that though. We went from 6.67 times 10 to the negative 11th, right? So decimal point, 10 zeros, and then 667, to 9 times 10 to the 9th. 9 with 9 zeros after that.
9 billion.
9 times 10 to the 9th.
Oh, are those Q's?
These are Q's.
Okay.
These are Q's, yeah.
Oh, so is K always going to be 9?
K will always be 9 times 10 to the 9th. It's always a constant. Always, always, always 9 times 10 to the 9th. So what I'm trying to say though is that you went from a really, really small constant, 6.67 times 10 to the negative 11, to a really, really big constant, 9 times 10 to the 9th. So that gives you a general idea. When we talk about different forces and what's stronger, what's weaker, the force of gravity is extremely weak compared to an electrical force. Okay, if two things are charged, they're going to have a much stronger force between them than anything having to do with their gravity. Okay? Alright, I'll pause and let you copy. Notice that it is still radius. It's still like before, this is between squared. That doesn't change. Okay.
Hey, am I not supposed to be recording?
I added to him, but don't worry.
Okay. Similar to we used to have we had gravity, the acceleration due to gravity, and the force due to gravity, right? And really, it was just mass times the acceleration due to gravity gave you force due to gravity. Well, same thing here. Okay, if you take away one of the charges, you can just talk about the electric field of one of the charges. Okay, so what we have is basically the same exact formula except we're missing a second Q. Alright, and EF it's not E times F, it's just I'm giving you the letter EF. Make life easier. And EF, electric field, will be equal to K times 1 charge divided by the radius. So wherever you are near that charge would tell you the average electric field you're feeling. Okay? But the same idea then. If you were given just the electric field and you want to know force, you could multiply by a second charge. Just like multiplying the second mass in that formula for universal gravity. Okay? I'll pause again. Thank you. You could replace the KQ1, Q2 over R squared here, or say the KQ1 over R squared with electric field if you needed to solve for force and you only had electric field, or vice versa. Okay, so realize that really this stands for the K, the first Q, and the over R squared on bottom. You might have problems where I say, what's the electric field of this if I give you the force and a charge? Okay, I might say, what's the force if I give you electric field and another charge? Whatever. Okay? Okay. Moving on. One little thing I want to show is electrostatic induction. If you had two objects, you don't actually have to touch an object to get it to be charged in a certain way. What these are two metal spheres. Okay? And if I have something that's charged, let's say I have something that's negatively charged, and I come closer to these objects, we have these two metal spheres that are touching. What would happen is, whenever you have something that's, say, negatively charged, when you go towards another object, all of the other electrons are going to want to push away, because like charges repel. Okay? All the positive charges are going to want to be pulled towards it, because positive charges attract. So what happens is, if I have this basically one piece of big metal right now, because they're touching, all of the electrons are going to be pushed as much over to one side as they can possibly go, and all of the protons are going to be pushed to the other side. So what you're going to have is this idea where it's already going to be polarized. Okay? Because I have this negatively charged, even though I'm not touching it, as I get closer to it, they're going to want to polarize. If all of a sudden I split those two metal spheres, what you'd end up with is one thing positively charged and one thing negatively charged without actually touching the object. Okay? So that's what we call an electrostatic induction. Give something a charge without actually touching it. To induce the charge. Fair enough? Okay. Now obviously if I just touched an object, if I had one metal sphere and I had this being negatively charged, and I touched a metal object that was neutral, I would give that a negative charge as well. Okay?
But it's only not touching?
To do electrostatic induction, it's not touchable. Mythbusters on this, where they talk about cell phones at a gas station. And really what they say is that talking on your cell phone while you're at a gas station will not cause an explosion. Okay? Smoking would. All right, that's a little different. But talking on your cell phone is not powerful enough, and that's just there's an electromagnetic field. Okay, anyways, there are fields out there that will be polarized on that, but it's not going to cause any problems. Okay? Now, what will cause problems is if you're at a gas station, there can always be a difference in charge. Realize that your tires are good insulators. So your car could have a different charge than the ground and the pump. And that's where there's been a lot of problems. Okay? So, especially during the winter, you'll have a lot of people that it's freezing cold. Okay? And so if it's freezing cold, it's not going to be as humid out, for one, which means electricity can pass a little bit easier. But when it's freezing cold, what they'll notice is that there's a lot of people that start pumping their gas, hop in their car, right, and just wait, stay in the car until it's done pumping. They hop out of the car and they go right to grab the handle of the pump. That's where it's dangerous. Because what you could have is while you're in your car, you could have a different charge than the pump. All right, and also when you're going in and out of the car, your clothes rubbing against the seats can cause that change in charge. So then when you go to touch the pump handle, you'll have a spark. Okay, and just the fumes coming out as you're pumping the gas can ignite, and you can have explosions. And there have been a lot of explosions where people are at a gas station and they have a charge and don't realize it, and they touch the pump handle and cause an explosion. So what you want to do is every time, whenever you're going to pump, either you can stay outside, or as soon as you get outside the car, before you touch the pump handle, tap the roof of your car. Okay? Tap the roof so that you can neutralize yourself and your car with the charge. Instead of having the shock or the shock come down when you touch the handle right away near the gas fumes, just tap it somewhere on the roof further away. Okay? With that said, also there's another big danger where people need to fill up the little gas cans. Let's say I need to go fill up gas cans for my lawnmower. Never ever fill the gas cans up while they're in the car. Okay? If you have a pickup truck, if you have a car, whatever, take them and put them on the ground. Because your car can have, again, because you have rubber tires, you have an insulator, your car can have a different charge. So there's been a lot of gas station explosions where people will they just set their gas cans on the back of their truck, and then when they go to pump gas into that, they get another shock or another spark, and it sets off another explosion. Okay, so electrostatics is something you really want to pay attention to when you're at the gas station.
I'm scared.
Should be. Okay. Any questions on that? That's it for electrostatics. I have a worksheet to give you now.
That's fine.
Heck yeah, dude.